Hello, welcome to Science Talk. I am your host and resident oceanographer, Jim Massa. I want to talk with you today what we see here. Nordic seas heat loss, Atlantic inflow, Arctic sea ice cover over the last century. This is a literature review paper. A whole bunch of authors were involved with this. And basically, they do an extensive, exhaustive review of the literature examining these issues. And it appears in AGU, as you can see right there, Review of Geophysics. I will, of course, leave the URL in the comment section. And for those of you who are interested in reading this in detail, you can then access it that way. I'm going to try and hit the major points, the major findings, and major summaries of what they're discussing here. Let's first look at the abstract. Poleward ocean heat transport is a key process in the Earth's system. We detail and review the northward Atlantic water, which is abbreviated AW flow, the Arctic Ocean heat transport and heat loss to the atmosphere since 1900 in relation to sea ice cover. Our synthesis is largely based on a sea ice ocean model forced by a reanalysis atmosphere from 1900 to 2018, corroborated by a comprehensive hydrographic database from 1950 onwards. Also, Atlantic water inflow observations from 96 onwards, and other long-term time series of sea ice extent, 1900 onwards, glacier retreat, 1984 onwards, and Barents Sea hydrography from 1900 onwards. The Arctic Ocean, including the Nordic and Barents Seas, has warmed since the 1970s. This warming is congruent with increased ocean heat transport and sea ice loss, and has contributed to the retreat of marine terminating glaciers on Greenland. Heat loss to the atmosphere is largest in the Nordic seas, about 60% of the total, with large variability linked to the frequency of cold air outbreaks and cyclones in the region. But there is no long-term statistically significant trend. Heat loss from the Barents Sea, about 30%, and Arctic seas farther north, about 10%, is overall smaller, but exhibit large positive trends. The Atlantic water inflow, total heat loss to the atmosphere, and dense outflow have all increased since 1900. These are consistently related through theoretical scaling, but the Atlantic water inflow increase is also wind-driven. The Arctic Ocean CO2 uptake has increased by about 30% over the last century, consistent with Arctic sea ice loss, allowing stronger air-sea interaction, and it's about 8% of the global uptake. And basically what they're saying is because there's no sea ice, you have the air-sea interface that allows for increased mixing. And of course, the Arctic Ocean is still kind of cold water there. Gas solubility increases with decreased temperature. So remove the ice cap, the air and the sea will interact, will mix, and you can mix in more CO2. Okay, now the plain language summary. The major flow to and from the Arctic Ocean occurs across the Greenland-Scotland ridge. The inflow is mostly warm Atlantic water flowing northwards and cooling gradually. After completing different loops within the Arctic Ocean, portions of this water eventually flow south as cold, freshened polar water. Now, what they mean by freshened is that the salinity is reduced. So you have it flows south as cold, freshened polar water at the surface, cold, dense overflow water at depth. We review and synthesize how the Atlantic water cooling evolved over the last century in relation to the Arctic sea ice cover. In the mean, 60% of the heat loss occurred in Nordic seas, 30% in the Barents, and only 10% in the Arctic seas further north. Arctic sea ice decreased last century, created more open water, and permitted stronger ocean heat loss. In other words, diffusion to the atmosphere. And we all know that that's because of the increasing temperatures of the inflows into the Arctic Ocean through the Fram Strait or even through the Bering Strait. Bringing in that extra heat, the heat actually either melts the ice, prevents the ice from forming, and when there's no ice, simply diffuses into the atmosphere. This is what they're referring to here. Ocean volume and heat transport also increase. That's an important point. Consistently with increased heat loss and increased wind forcing. Ocean temperatures have generally increased in many areas during the last 50 years, and on Greenland, this drove the retreat of marine terminating glaciers. Variability in ocean heat loss to the atmosphere was primarily driven by cold air outbreaks and cyclones in the Nordic and Barents seas. And that explains variability in the Arctic Ocean CO2 uptake being 8% of the global amount. The individual, so now they get into the introduction and the focus, what they're trying to do here. The individual seas of the Arctic all lose heat to the atmosphere when the yearly average is calculated. The heat loss and associated land and water circulation have been widely studied due to important consequences for each regional sea, the Arctic climate as a whole, and the global ocean circulation. The actual surface heat flux is only measured in short periods over a limited area and varies over time and region in profound ways. The main goal of this paper is to quantify and describe this heat loss, why it has increased over the last century, how it relates to sea ice cover, CO2 uptake, and atmospheric circulation, as well as the general warming trend from climate change. While it's been known for more than 100 years that Atlantic water is the primary heat source for the Arctic Ocean, going back to Helen Hansen and Nansen in 1909, much of the variability, trends, and related consequences are still undetermined. So here's figure 1, which is a schematic overview of the relationship between the warm Atlantic water inflow across the Greenland-Scotland ridge and its influence on 1, Nordic seas heat loss, deep and dense water outflow, that's 2, 3, the CO2 uptake, and 4, Greenland melting, and 5, Arctic sea ice cover. The vertical red arrow illustrates the large cooling in the Nordic Sea, the orange arrow, the smaller cooling in the Polar Sea. The eastern half of the Arctic Ocean, the Barents Sea is not covered, but the area in bathymetry is correctly scaled. The cyan arrow represents the systemic sea ice drift toward the Fram Strait. Take a little larger look at it. Okay, so here's the warm Atlantic water inflow. As you can see, they're indicating about 9.5 sphere drips. So that's coming in this way. And this is right here. You can see it's intermediate, goes a little below. This is some very deep water that fills the basins. So here is going through the Fram Strait. This is the Lomonosov Ridge. And this is the Bering Strait seaside. There's Alaska. So this would be the Chukchi, Beaufort, so forth. And there's so we got some heat loss here. This is a major heat loss. And then as it circulates, it cools down, maybe gets a little freshened, and flows back out. And that's what this cold, dense water outflow represents. CO2 uptake, because you have open water, the CO2 in the atmosphere mixes with the water there. There's the influence on Greenland. That purple is the cold polar water outflow. So you have the cold dense water outflow. This is deeper in the column. That's about 3.3 sphere drips. Cold polar water is about 1.9 sphere drips. And then you have the Canadian outflow, basically going through the archipelago. And that's about 1.7 sphere drift. So if you add this all up here, let's see if I can do math in my head. Basically, you have, this looks like 5.2, it's about total of 7 sphere drifts of the outflow, and you got 9.5 of the inflow. So you got about a difference about 2.4, 2.5 the sphere drift, and then you have inflow coming in from the Pacific side. So basically, what this is telling us is, preservation of volume kind of has to balance out. So you might lose some through evaporation. The water evaporating into the atmosphere. Maybe some sinks down through the water column to ventilate. So they're probably not showing any of the ventilation that's taking place over the basins, within the basin, and so on. But this does eventually have to equalize. But you get an idea from a modeling point of view. We can see that the main heat is coming in. Now, this ain't cold Pacific water inflow. Well, we now know that this amount is increasing, but it's also getting warmer. So it's probably still a temperature less than the Atlantic water flowing in, but we do know that the water coming in through the Bering is also increasing in temperature. So that's kind of giving a little schematic to kind of give you an idea of what's happening. Most important consequence of ocean heat loss is that when seawater cools, it becomes denser. Yeah, we know that. The heat loss in the Arctic Ocean is thus the primary driver of the transformation of the warm inflowing water into dense water that fills the North Atlantic at depth. And that is a reference to this cold, dense water outflow. Cooling also increases the CO2 solubility. We know that. Gas solubility increases with decreasing temperature, such that the Arctic Ocean is an important sink of CO2. If the water column is strongly stratified or the surface water sufficiently fresh, cooling leads to sea ice formation, which dramatically changes energy momentum and biogeochemistry fluxes between the ocean and the atmosphere. So the heat loss dictates variability in the Arctic sea ice cover, but also works the other way with sea ice regulating heat loss. If less heat is lost to the atmosphere, the heat remaining in the ocean can result in increased melting of sea ice further downstream or increased melting of marine terminating glaciers, with potential implications for ice discharge from the Greenland ice sheet. Finally, heat loss itself is driven by atmospheric condition. That is a reference to the Arctic dipole, the Arctic oscillation, North Atlantic oscillation, which are clearly modulated by temporal and spatial changes of the wind field in different regions. We hereafter use the term heat loss for the spatially integrated surface heat flux over a region like the Nordic seas, given in terawatts, which is 10 to the 12th. And use the term heat flux, meaning the specific value at the surface for a smaller area of an observation in the unit watts per square meter. Okay? A flux is having some sort of flow rate given whatever units per whatever units of measure of area, and usually it should also include per unit time. So you might want to say they probably should have said heat flux watts per square meter per second, per hour, per day, what have you. That would have been a little more accurate. Go through table 1 where they break down the location, give you the area, and they give you the heat loss and the heat flux. Watts per square meter. I would like to see a unit time indicated there. Then I give a little explanation saying heat loss is the heat flux multiplied by the area of each sea. The CO2 uptake is estimated as described in the methods based on heat flux and sea ice concentration. All values, including sea surface temperatures and sea surface salinities, are averages over the sea shown in Figure 2. Heat loss trends that are significant at the 95% level is indicated by an asterisk, where P value is less than 0.05. They go on to say, what region they're looking at. And Figure 2, the mean simulated Arctic Ocean volume transport and heat loss. Northward red arrows and southward flows are blue arrows, a scale so that the width represents volume transport in sphere drops. There's that 9.5, indicated in what we looked at earlier. The heat loss in the Nordic seas, the Barents Sea, and the Polar Sea in terawatts. The Cyan region represents the annual mean sea ice transport. It's about 1 million square kilometers from the polar seas to the Nordic seas, given by a white arrow. That would be this right here. The heat is released to the polar sea atmosphere when the sea ice forms, with subsequent loss of heat from the Nordic seas when the sea ice melts, contributing to the 115 terawatt cooling indicated in the figure. Okay, so let's take a little larger look at that. And you can see here's the main inflow. And you can see about 3.2 sphere drops heads over towards the, looks like the Kara Sea. Some goes further, circulating up, makes it towards the Laptev, and so on. Here's the heat coming in through the Pacific side. The pale blue shows how these are all shallow shelf areas that during the ice ages, when the sea levels drop, you basically have just a little sea here. This would be all land. And here are some of the outflows. There's that, going through the Canadian, let's see if we can pull it up this way. Yeah, that's this Canadian outflow here. So they're showing that here, as well as here and here. And then here's the ice flow that they indicated. And then they give you how much terawatts is happening. You see, most of it is in this small area because this is where the warm water comes in, so it's going to cool off first. The Arctic Ocean acts like a double estuary. This implies that Atlantic water is the main inflow. You have two major outflows: fresh polar water at the surface and dense overflow water, abbreviated OW, in the deep. The concept of the Arctic Ocean as a double estuary dates back to Stijsbrand. I don't know if I'm pronouncing that correctly, or Stigebrand, who also estimated the two main outflows across the GSR, it's Greenland-Scotland Ridge. From observations of the Atlantic water inflow, a total net transport of about 8 plus or minus 0.7 Siedrups across the GSR has been estimated between 1993 and 2017. The two secondary inflows are relatively minor, bringing about 0.8 sphere drops through the Bering Strait, and they're referencing Rebecca Woodgate's work, and about 0.1 sphere drops from river runoff. The total inflow is balanced by a net southward flow of polar water through the Canadian archipelago, and southward flow of both polar water and overflow water across the Greenland-Scotland Ridge. Okay, review of relevant processes and conditions. Over the last 100 years, estimates of Arctic Ocean heat loss to the atmosphere have evolved substantially. Thanks to the early Arctic explorer oceanographers and long history of fishery-related surveys, there are century-long observational records in the region that document how these waters have changed over time. And I refer to Mosby in 1962 reported the mean hydrographic properties, volume, and heat budgets of the regional seas based on observations from the MOD expedition. Many estimates were close to present values, and the Atlantic water inflow was identified as the largest heat source. Makes sense. However, as we will present here, the Atlantic water inflow volume estimate of 3.6 was probably half the correct value, and the 90 terawatt heat loss of the Polar Sea much too high. Bjerknes found that the atmosphere generally forces the ocean via the exchanges of heat and momentum, but also that ocean temperatures can influence the thermodynamics of the atmosphere. It's long been evident for a long time that the North Atlantic dominates northward overall heat content, so OHT, in a global perspective. This dominance was consistently quantified to be 15 sphere drifts and about 600 terawatts across 45 degrees north latitude based on global hydrographic data. Recently, Lozier found that a similar volume makes as far north as 58 north. Let me discuss atmospheric forcing of heat loss. The general regional circulation within the Arctic Ocean is driven by wind stress. They go on to say that they focus on the inflow. There is pronounced seasonal cycle in the ocean heat loss around the annual mean, driven predominantly by radiation. It is indeed only from September to March that the ocean loses heat to the atmosphere. From April to August, the ocean gains heat on average, thing called the sun. Ice melts back, and then it gets a lot of direct solar insolation. The downward surface heat flux peaks in July about 100 watts per square meter, while the upward heat loss is more evenly distributed throughout winter. Ocean heat loss exhibits variability on a range of other timescale, large year-to-year and to annual variations, owing mainly to the large internal variability of atmospheric heat transport. On decadal scales, Bjerknes hypothesized that there is strong compensation between the ocean and atmospheric heat transport. This mechanism, called the Bjerknes compensation, was later confirmed for decadal and even longer timescales. And the reason for the large variability is due to weather. That's pretty much what they move on to say here. Okay. Then they discuss, as I said, for those who want to read the article in detail, just click on the link here. I'm going to just hit highlights here. Arctic sea ice loss is now apparent throughout the year, but the amount of loss varies depending on season and region. For example, we now know that the sea ice on the Eurasian side is disappearing much faster than the sea ice on the North American side. Diminishing sea ice has a number of important consequences for marine ecology and navigation. It plays a part in Arctic amplification and decreasing surface albedo acts as a positive feedback on global warming. Okay. When I did my video on ice algae, I explained how the loss of sea ice creates two major losses of productivity. One, the algae on the underside of the ice itself. That's you have that algae there that's doing its thing. Photosynthesizing, creates a little ecosystem there. Well, if you lose in the sea ice, you're going to lose the ice algae community. Also, if you lose in the sea ice, you lose the ice melt, because when the sea ice starts melting, you get the ice edge, ice melt productivity. We start losing that. So then what are you left with is the open ocean productivity, but the diatoms can't really do their thing until the sun is at a sufficiently high enough elevation to activate the electron transport chain system within the chloroplast so that the photosynthesis can occur. So basically three major sources for productivity: ice algae, ice edge productivity, and then open water productivity. Well, if you start losing the sea ice, you're going to lose the first two. So the overall effect will be a decrease in productivity, which then has negative ramifications for the ecosystem writ large. There is a nearly linear relationship between the global atmospheric CO2 concentration, increased long wave radiation. Sunlight comes in, and the short wave radiation reflects back out on the long wave radiation, and Arctic sea ice extent, appearing in both observations and coupled climate simulations. During late spring, summer, early fall, the largest ice loss is found inside the polar sea, causing a profound change in surface fluxes there. The additional solar heat gained by the ocean during this time of year is lost to the atmosphere before and during sea ice formation in the cold season, resulting in a small net change in the annual mean heat fluxes. So there is an increase in the annual cycle of summer heat gain and winter heat loss within the polar sea, but there has until today been little change in the net annual heat loss, according to Onaheim in 2018. This is different for the regions experiencing reduced winter sea ice, which up to now has mostly occurred in the Greenland and Barents Seas. Well, we're now finding that next is the Kara Sea. The Barents Sea is pretty much like nearly ice-free year-round. The Barents Sea, the Kara Sea is next, but we're seeing a lot of reduced winter sea ice in the Laptev and East Siberian seas. So, especially on the Eurasian side, things are rapidly changing. We are losing the sea ice. A clear relationship between overall heat transport and sea ice cover variability has been established for the Barents Sea, basically what I said. Here, an increased overall heat transport leads to reduced winter sea ice cover, stronger ocean heat loss. That means the warmth in the ocean goes to the atmosphere, and increased dense water production. That loss, that heat goes into the atmosphere, the water cools down, becomes more dense. That's basically what they're saying there. There is evidence that a similar mechanism is now at play north of Svalbard, which is getting into the Kara Sea region, and in the eastern Eurasian basin, and they cite my friend Igor Polyakov. Increased Atlantic water inflow leads to less sea ice cover, also in the western Nordic seas. As a result, the East Greenland current flowing southward along the Greenland slope is now partially exposed to the atmosphere in winter, so that water mass transformation directly within the boundary current may occur. These new areas of open water allow for more local heat loss and dense water formation, and may alter the properties and composition of the overflow water at depth. However, while this is important here, while the loss of winter sea ice may cool the ocean more locally, it also stops brine from being released during ice growth. The overall and net effect of less winter ice on dense water formation is thus not obvious. The convection will only occur under strong heat loss if the surface is sufficiently saline and thus dependent on stratification, often reflected in winter sea surface salinity. So then the Arctic Ocean can largely be viewed as an enclosed basin, the Arctic Mediterranean, as Elvevik and Nilsson put forth, with the GSR as the gateway to the Atlantic in the south. Consequently, oceanographic conditions in the Nordic Sea are heavily influenced by the northward flowing Norwegian Atlantic current transporting warm, saline Atlantic water across the Greenland-Scotland ridge. There's Atlantic inflow to the Nordic seas. The atmosphere's forcing is instrumental in driving the ocean circulation in two ways. First, heat loss to the atmosphere cools the Atlantic water inflow within the enclosed Arctic Ocean and densifies the water as it progresses northward on the eastern side of the Nordic Sea, circulates cyclonically in the Arctic boundary current. This cooling thus contributes to the mean circulation. but variability in cooling may consequently also drive variability in flow. Second, surface wind stress both drives the mean cyclonic circulation, cyclonic is basically counterclockwise, as well as inflow variability. Wind forcing clearly influences the short-term Atlantic water inflow variability across the Greenland-Scotland ridge. Heat fluxes and cooling of the Atlantic inflow. Our understanding of the cooling of Atlantic water as circulates the Arctic Ocean has improved over the last decades. Simonson and Haugen highlighted the Barents Sea as an area of effective heat loss to the atmosphere, approximately 42 to 162 terawatts, in addition to the Nordic Sea, 220 to 250 terawatts. But there's some, at the time, uncertainties in estimating these surface fluxes. And they go on to basically do a brief literature review of looking at the heat fluxes in the Arctic Ocean. So a central question is the relationship between the Arctic Ocean heat loss and the mass heat and freshwater flows in the region. And the result was this figure here. The simulated total annual heat loss of the Arctic Ocean in blue and the three subdomains, green, black, red, by the Norwegian Earth System Model. That's the NESM that you often may see in papers. That's the Norwegian Earth System Model. The simulated annual mean ocean heat loss in terawatts are presented here. The mean cooling of the Arctic Ocean is 187 terawatts. For the Nordic seas, the 15 years of highest, the black crosses, and the lowest, the blue crosses, annual detrended heat losses are indicated. So let's look at this in larger detail. So this is the ocean heat loss in terawatts. So you have the Arctic Ocean, green is Polar Sea, the black is the Barents Sea, and the red is the Nordic Sea. Now, when you look at this, okay, so here's the here's the results here, and you can see the seasonality in the values. The straight line is the regression line fit through the data here, and you can see that for the Arctic Ocean, we have a positive slope. That means there's more heat loss to the atmosphere. Now, the heat loss to the atmosphere is increasing. Why? Because there's less sea ice. We see a positive slope for the Barents Sea. We now know the Barents Sea is pretty much ice-free year-round. Now, I don't know the exact equation but this almost looks like a flat line. It might have a very small slope to it. I don't know if the slope will be significantly different from zero. If it's significantly different from zero, then we have a trend. If it's not, that means we have a flat line and really no relation here. Through the Polar Sea, looks like it's a slight positive slope there. It would be helpful to see the actual regression equations. But we can see the high heat loss years and then the low heat loss years. But the take-home message from that is heat loss to the atmosphere is increasing, and that's because it's either melting the ice and or there's no ice there, it just diffuses right into the atmosphere. That's what this is telling us. And I go through a bunch of equations here. We don't need to, that not for our purposes of discussion here. Again, those of you who wish, have at it. Transformation of Atlantic water into overflow water and polar water. The Atlantic water inflow across the GSR may undergo a variety of transformations within the Arctic Ocean before returning south. Some of it returns south without undergoing much cooling. forming what was known as the Atlantic water outflow. And it's about 3 teardrops of that. A small amount flows south in the eastern part of the Denmark Strait. The remaining GSR outflows either fresh and cold polar water or the denser overflow water spilling across the ridge between Greenland and Shetland. Okay, so basically applied regression and associated statistics for calculating ocean CO2 uptake, and they present some functions here, an R square, and then a p-value. Depending what the p-value level is, if you choose 0, the 5%, the 95% significant level, in other words, p-value less than 0.05, all three are significant. If you choose p-value less than 0.01, that's the only significant one there. Mean ocean transports in various Arctic sections, and so negative is flow in, positive is flow in, negative is flow out. And it gives you the heat going in, or the heat that's either lost or gained. Okay? So note, positive volume transport values are northward. Ocean heat transport is relative to 0C for all sections. A positive ocean heat transport with a negative southward volume transport implies that the temperature is lower than 0C. Okay. That means it cooled down. Heat convection in Greenland Sea used to produce the coldest and densest bottom waters in the Arctic Ocean due to combined effect of severe winter cooling and sea ice formation. That is, when we zoom up here quickly, that's referring to dense bottom waters in the basins. Okay, there we go. However, since the early 1980s, only convection to intermediate depths has been observed. This is important. If you can go all the way down to the bottom, you can ventilate the entire water column. If you're only getting to intermediate depths, there's the risk of the deep water in the basin eventually becoming anoxic. It's not going to be ventilated. But also that's telling us what? That the water is not as dense, that it's still warm enough to not cool down enough to sink sufficiently far down enough. So this is changing. Even with the increased salinity, it only finds its buoyant forces at intermediate depths. A main reason for this change is the retreat of the sea ice edge towards Greenland. The retreating sea ice has led to reduced brine release over the central Greenland Sea, and in combination with reduced atmospheric cooling, this may limit the formation of intermediate water masses and overflow water supply. So in other words, there are changes, because of the Atlantification that's going on, there are changes to the water property itself. And the implication is that we're going to start seeing a different stratification regime. We might see how the halocline is being affected, and I've discussed this with you guys before. So there are definitely changes to the oceanographic conditions taking place within the Arctic Ocean. Okay, figure 4. Simulated annual mean surface heat flux given in watts per square meter, warm colors, and sea ice concentration, cold colors. In other words, blue, red, right? The dotted blue lines there shows the location of the Greenland-Scotland Ridge. Okay, so let's take a little bigger look at this. And Here's Iceland, right? Greenland, right? Fram Strait and all that kind of good stuff. Obviously, we have warmer waters here in the North Atlantic. Starts cooling down, but look how warm, all that warm water coming into the Barents, and the temperature is increasing, the flow rate is increasing. That's contributing to the Barents basically becoming almost ice-free now, year-round. So this is net surface flux. So the flux is watts per square meter. So this is how much heat's going to the atmosphere. And then they give you the sea ice concentration. The whiter it is, the thicker the ice. The bluer it is, the less ice there is. And that's kind of what we see here, less ice. There's Novaya Zemlya, right? And Severnaya Zemlya. And then we see it on the opposite side over in the Pacific. So it's showing some heat being, moving into the atmosphere. Arctic Ocean CO2 was first determined by Lundberg and Haugen in 1996 based on volume flows and inorganic carbon observation. They inferred a net uptake of 110 megatons of carbon per year. Similar approaches have been applied to the other individual seas based on more recent data. For example, McGilchrist et al. In 2014 inferred a net uptake in the polar ocean and Barents Sea of 166 megatons of carbon per year, while Jensen et al. In 2011 determined a net Nordic Seas uptake of 190 megatons of carbon per year. The CO2 uptake has been estimated from observations of the CO2 partial pressure in the ocean surface, allowing for direct computation of the air-sea CO2 flux, as described, for example, by Takahashi et al. In 2009. For the Barents Sea, Omar et al. In 2007 determined flux densities in a range of 3.4 micromoles of carbon per square meter day in the winter to 21 micromoles of carbon per square meter day in the fall. These estimates were extrapolated to the entire Barents Sea by Kivamai et al. In 2010, yielding a net uptake of 58 megatons of carbon per year. East of the Barents Sea, CO2 outgassing may occur, a consequence of the decomposition of terrestrial organic matter supplied by the large Siberian rivers. I would also add that the Barents Sea is warming. So if it's warming, warmer water, gas solubility decreases. So that may also be forcing the CO2 to outgas. I would add that factor in as well. Across the Bering Strait, the Chukchi Sea is highly undersaturated in summer because of ample biological productivity. In other words, the phytoplankton, the primary producers, are utilizing the CO2. And uptake of CO2 has been estimated to be 13 megatons of carbon per year over the ice-free season, much of which is exported to the halocline and deep waters over the winter. Okay, and they go on to discuss other aspects going on there. Reviewing available literature at the time, Bates and Mathis in 2009 determined net annual air-sea flux in the polar and Barents Seas to between 66 and 199 megatons of carbon per year. Recently, Yasunaka et al. In 2018 mapped all available partial CO2 observations in this region and determined an annual uptake of 180 plus or minus 130 megatons of carbon per year. That's a big range. So they extracted fluxes for the Polar Sea and Barents Sea, as defined in this paper, and they obtained a mean flux of 149 plus or minus 107 megatons carbon per year. And they proceed to give values of the average flux of 8 to 16 micromoles of carbon per square meter day. Many processes influence Arctic Ocean CO2 uptake: primary production, organic matter remineralization, biogeochemical processes during sea ice formation, melting, etc. Then they go into section of what the methods that they used. This is the NESM simulations like I showed you earlier. Then they describe how they looked at the atmospheric forcing, available observations. Again, those of you who are interested, click on the URL. So what I want to look at is showing the net ocean heat transport in terawatts. And the black is the Bering Strait. You can see not much happening down there. It's very low. The Canadian archipelago in gray. The Greenland-Scotland Ridge overturning. So that's the mixing, the ventilation. And then there's the gyra aspect. And then the pale, I guess green, is the total. What is important to note is the trend from 1900 to about 2010. Follow the cursor right here. Follow that. That is increasing. That has positive slope. This is, of course, reflecting seasonal variability. But overall, this has positive slope, telling us that the heat transport is increasing. A major reason why the Arctic is warming up. So we see this clear trend right here. So the simulated annual mean Arctic Ocean heat transport, the contributions from the individual straits are calculated using 0C as a reference and show what I just indicated to you, the Bering, the outflow, etc. The dashed line that we see here is the total Norwegian Earth system model, Japanese reanalysis. Figure 6. Okay. This is, I'll get to this in a moment, but first let's go through the description for the figure. Observe the simulated Nordic Sea's thermohaline water mass properties since 1950. Geographical regions with color coding are marked in the map. The TS range, that's temperature salinity, for each water mass is based on the frequency of occurrence and indicated by the colored patches outlining 60% of the observations. Colored-filled dots show observed median values, and related arrows show the linear trends from 50 to 2019, the basic 70 years. Similarly, colored stars show simulated NESM median values, and related arrows the linear trends for a 60-year record. Vertical constraints for defining the water masses are as follows. Atlantic water and returning Atlantic water by the depth of maximum temperature below 100 meters. Overflow water by density above 27.8 kilograms per cubic meter and above the sill depths of 650 meters for the Denmark Strait, 840 meters for the Faroe-Shetland Channel. Intermediate water by the typical mixed layer depths of 150 to 350 meters in the Iceland Sea, 500 to 1,500 meters in the Greenland Sea. That's getting pretty deep. So, let's look at this. Now, this is what's called a TS curve. You have temperature on one axis, typically by convention taken to be the vertical, and then you have salinity, PSU, practical salinity unit, typically on the horizontal. So, and these lines that you see here with the values of 27.2 and 27.4, etc., this is isopycnal. These are lines of equal density. So, and these densities are going to be units of kilograms per cubic meter. I did a video on salinity and said all about salinity. You might want to check that out. So they have the color codes here, and then they kind of show you where it's taking place here on the map. So you got the Faroe, you got the Svino, however that's pronounced in the Scandinavian languages, the Barents Sea opening, the BSO, and the Fram Strait East, Fram Strait West, Denmark, etc., etc. So what they're showing here is basically the mixing and the density distribution. So higher density is down here, so this has a higher density. This location looks like the Greenland Sea than, say, here in the Fram Strait. This is showing you the distribution, And this is also showing you the mixing regime taking place between the various water masses. If you had a discrete point, then that means you have identified a discrete water mass. When you start seeing this diffusing, that indicates mixing is taking place. And this gives you an idea. You can line up the colors here with here. For example, if I look at this light blue here, that's over here, and that gives you an idea of the temperature, the salinity, and thus the density. Denser water will sink, obviously. And then figure 7 now looks at the uptake of CO2 in megatons of carbon per year as a function of the NESM, surface forcing. For the Barents and polar seas, the most important parameters is sea ice cover, whereas in the Nordic seas, heat loss is best at explaining observed variability. Negative values show ocean uptake of CO2. Areas used to convert fluxes into megatons of carbon are from table 1. So let's take a look at this. Blue is the Arctic Ocean, green is polar seas, black is Barents Sea, red is Nordic seas, and as they said here, the ice cover or heat are going to be the main drivers of the fluxes. If you have ice cover, the fluxes will be decreased. If there's open ice, where you have fluxing of heat, that's going to be a driver of CO2 uptake because the water then cools down, allowing for increasing mixing and increased dissolution of CO2 into solution in the water. Now, it's interesting to note that in recent years, the uptake in the Barents is declining because the Barents Sea is warming up. That's why we see this decline here in recent years. In fact, overall, probably from about 1960 onwards, but most dramatically in recent years. So that's the reason for that. The Barents is warming up, warmer oceans, warmer water, gas solubility decreases. And here is basically showing where cold air outbreaks take place, extratropical cyclones, basically rotating in the counterclockwise. This is tied into what the North Atlantic Oscillation and the Arctic Oscillation, and also the Arctic Dipole, what they're all doing and how they're interacting. And you go on to CO2 observations, new estimates, and again they go do an explanation, do a little literature review, and basically say, we need to use chlorophyll as a proxy for biological production. That's pretty much, when we estimate productivity, we're actually looking at the chlorophyll concentration. Because chlorophyll is doing what? It absorbs, lights in the other areas of the visible spectrum, but reflects what? Greenback, visible spectrum in the green region, that reflects that out. So we measure that. We actually look at, that specific wavelength, and then we can get an idea of the chlorophyll, which then is an indication of how much phytoplankton activity is going on. Ocean ice sheet interaction. The heat loss to melting Greenland's marine terminating glaciers and iceberg is not directly represented in the NESM in the absence of an interactive ice sheet model. Freshwater fluxes from Greenland are thus prescribed in a similar manner as Arctic rivers using mean values before 1958 and values from Bamber et al. 2018 onwards. Modest magnitude of this heat loss, about 1 terawatt, suggests that the direct impact of the ice sheet on the Nordic Sea's heat budget is small. Importantly, the Nordic Sea's heat content impact on the ice sheet may be significant and has been quantified using simulated ocean temperatures over the northeast Greenland continental shelf. We use the parameterization prescribed by Slater et al. In 2019 to quantify the advance and retreat of Greenland's glaciers driven by oceanic forcing. Parameterization utilizes a summer liquid freshwater flux per glacier from the regional climate model, together with mean annual ocean thermal forcing, TF, thermal forcing. Calculated as the ocean temperature above the in situ freezing point between 200 and 500 meters depth. And then they go into a big result section here. Some of the Atlantic waters contribute to the melting of sea ice and glaciers, or it is mixed with river water, becoming sufficiently fresh to exit the GSR at the surface instead of being more saline and thus more dense and sinking down. And so it's fresher polar water. Centennial means from 1900 to 2000. Surface cooling. The warm northward flowing AW is cooled by the overlying atmosphere. The heat is transferred to the atmospheric boundary layer as sensible, latent, and radiative fluxes and ultimately radiates out to space as long wave radiation. Because the winter season is generally colder and longer the higher the latitude, one might expect the heat fluxes to be larger in the polar sea than further south. This is not the case. Heat loss from the polar sea is effectively restricted by the nearly permanent ice-covered sea. And we now know this is being reduced, so expect this to change in the upcoming years and decades. The Nordic seas lose the most heat with a centennial annual flux of 115 terawatts, based on an average surface heat flux of 45 watts per square meter. All the heat loss and surface flux values presented here are simulated annual means unless otherwise specified. The Barents Sea has a smaller surface area and a lower surface heat flux, so the centennial mean heat loss adds up to 57 terawatts. Furthermore, the much larger area of the polar sea has a surface flux of lower than 2 watts per square meter, resulting in a heat loss of only 16 terawatts. Okay, now we'll come to some important information here. Sea ice prevents heat loss in two ways. First, it forms an effective insulating layer by its low thermal conductivity. Second, when sea ice forms at the surface, the latent heat is released into the atmosphere and is entirely used to grow the sea ice. This means that the ocean temperature only decreases at the time and location where the sea ice melts. In the polar sea surface layer during winter, the temperature is already at the freezing point and cannot get colder. A volume flux of only 2,000 cubic kilometers per year of the polar sea ice drifts southward through the Fram Strait into the Nordic Sea with the East Greenland current and melts there, a process termed sea ice export. Now, remember, this is controlled by the Arctic dipole, the positioning of the high and low pressure system in the Arctic dipole, and the related wind stress, how the wind pushes on that. If conditions are right, yes, the ice gets pushed out the Fram Strait. But if conditions are not right, there's a switch in the dipole and how it oscillates between the locations of the high and low pressure system, the sea ice will then be retained within the Arctic Ocean. They report a sea ice area exported out through the Fram Strait about 1 million square kilometers. The heat gained by the polar sea atmosphere during the sea ice formation thus cools the Nordic seas when it melts. The heat transport carried by the sea ice export is estimated to approximately 17 terawatts. So the exported latent heat and direct polar sea heat loss are comparable in magnitude. The atmosphere above the polar sea thus gains about 33 terawatts. The export of 17 terawatts of sea ice in addition to the 16 terawatts directly lost from the ocean. What they're basically saying is the atmosphere is warming. At least it's warming, at least seasonally. And basically go on to say the Nordic Sea's heat loss has remained quite constant over time. Ocean temperature and sea ice extent. The temperature of the Atlantic water inflowing across the GSR is close to 8C, and clearly the warmest water in the Arctic Ocean. The highest AW temperature is found at the surface in Nordic seas, but inside the Polar Sea, the maximum is located below the fresher and colder surface layer. What that means is it's more dense, so it slides under. The two Atlantic water branches are clearly visible in the sea surface temperature and sea surface heat flux. One branch flowing eastwards into the Barents, one flowing northwards west of Svalbard, which is the West Spitsbergen current. The only other poleward flowing water mass is the Pacific water in the Bering Strait. The temperatures are much lower, but it's still greater than 0C, so it's still bringing in heat. Ocean heat transport, about 179 terawatts, is close to that of the surface cooling 187 terawatts, dominated by the net heat transport across the GSR of 172 terawatts. Pacific inflow is about 0.7 Seerdrups. Most of this leaves the Arctic Ocean through the Canadian archipelago, which has a net southward volume transport of about minus 1.7 Seerdrups. The volume budget is closed by the net southward transport across the GSR of negative 8.5 Seerdrups. With this closed volume budget, a simulated Arctic Ocean heat transport value, 179 terawatts, is obtained. Now let's look at figure 9. Simulated properties of the Greenland-Scotland Ridge outflow. Panel A shows the contribution in percent to the GSR outflow as a function of temperature and salinity. The outflow is divided into three main water masses: overflow water, polar water, outflowing Atlantic water. Panel B shows annual mean volume transport in Seerdrups, and C is potential temperature for each water mass, and then color coding similar to what we saw in a previous figure. So let's look at this. So once again, we have basically a TS curve, and these are isopycnals showing lines of equal density getting more dense as we move from left to right. So here's the overflow water, here's the Atlantic water. Okay, we see the Atlantic water is about 8C, so it's going to be warmer. Right? We see some cooling down here. Here's the polar water, right? The overflow water. So we can see that the overflow water has the highest density. We can see that right there. The Atlantic water. Let's follow the isopycnal, 27.6. This is about 27.8. Yeah, so Atlantic water is also pretty dense, but not as dense as the overflow water. The polar water, polar water has some of the smaller, the lower density values. So here's the volume transport. The light blue or cyan is the polar water. The dark blue is the overflow water, and the red is the Atlantic water. And we can see the seasonal variability in all of them. And then the potential temperature. No surprise here, the Atlantic water is the warmest. And then the polar water generally is the coolest. But TS curves is an important tool for us oceanographers, because if you know the density, you get an idea of sinking and mixing, and therefore movement. and you can then calculate the transport sphere drop. You can calculate from that fluxes. There's a whole bunch of information that can be obtained from looking at TS diagrams. Hydrography and dense water formation. The inflowing AW is transformed into denser but also fresher water. This means that cooling is the ultimate driver of densification. The progressive observed cooling and freshening from AW to OW are clearly illustrated in Figure 6. Let's take a toot back up there. Only this thing would scroll faster. Figure 6, right? We can see this happening here. It's getting less dense, moving, up in this direction. So as it's flowing, it's cooling down. But we're now seeing something different happening now. Because of the loss of the sea ice, the mixing now is being reduced, and the intermediate water is actually staying at intermediate levels. And so it's retaining a higher salinity value. That's a trend that we're seeing in recent years. More than 60% of this cooling has occurred before the Atlantic water subducts beneath the fresh polar water in the Fram Strait. In other words, subducting is going underneath the surface layer, going into the intermediate layers. And they proceed to go into some of the, they get into the weeds here, looking at the diffusion and the mixing, etc. Atmospheric circulation heat loss. The largest heat flux, surface heat flux is largest over the northward flowing Atlantic water between the GSR and the sea ice. The heat loss increases towards the north in Fram Strait west of Svalbard and in the Barents Sea. The spatial pattern of this heat loss north of 60 north is very similar between these two models. And you look at CO2 uptake for the Arctic Ocean. We touched upon that earlier. Variability and trend for this 100-year period. And then they basically are looking at atmospheric circulating heat loss in this 100-year period. That's what this section will be looking at. The overall heat content of Atlantic water has varied due to changes in volume transport, increasing, and temperature over the last century, increasing. Primary reason for the steady increase from about 150 to 200 terawatts is an enhanced flow across the GSR of about 1 sphere drops. And if you go back, I've done videos discussing a lot of all these things here. So you can kind of think about like this, what we're doing here is kind of coalescing, synthesizing, pulling all the information I've been presenting to you in these videos, trying to pull it all together into one big package, if you will. Nordic Sea's heat loss remain quite constant despite a large increase in poleward overall heat content. The century-long heat loss trend of plus 6.2 terawatts per century is only about 5% of the total heat loss, quite small, not significant. This implies that the Nordic seas have warmed, but that heat now reaches further poleward. This is important. The Nordic seas have warmed, and we know they have, or that the heat now reaches further poleward. Notice that heat is being carried further into the Arctic Ocean. The annual mean Nordic Sea's ice cover dropped from about 700,000 square kilometers around 1900 to about 500,000 kilometers in the late 1970s. And by the way, see the period here? They're using the European Convention. We would, in America, we would have a comma there. If they wanted to say 700.23, then they would have 700, 23. The Europeans, the convention is reverse. Where we use a comma, they use a period. Where we use a period, they use a comma. That's how it is. Again, sea ice cover has been quite stable since the 1980s, with values in a range of 400 to 450,000 square kilometers, but this is now decreasing, as we know. The main reason for the sea ice decrease is not a reduced heat loss, that remained fairly stable. The annual changes of Nordic seas heat loss are thus also unrelated to sea ice area. And they give a correlation coefficient of minus 0.9, which isn't really that great. They're rather explained by variation in atmospheric circulation. I'm probably going to quibble with that. We know that the increased heat, is affecting sea ice. We know that. Now, this could be that because they're looking at this 100-year period. So it could be that for that 100 years, that would be a correct statement, but we know a lot has changed within the last 20 years. So perhaps I think that's what's going on here. They're talking about what's going on for that 100-year period, but when you look at the last 20 years, then yeah, we know that all this extra heat, because of the significant increase in heat content, is what's driving a large part of the reduction of sea ice. Barents Sea heat loss has increased steadily over time, and that's why congruent with Atlantic water temperature and a decrease in sea ice cover. Yeah, the Barents is becoming Atlantified, and the sea ice, there's practically no cover there. It's pretty much gone year round. The increased heat loss corresponds to an increase in area average surface heat flux from about 30 watts per square meter around 1900 to about 50 watts per square meter around 2000. That has since increased in the last 20 years. This is first and foremost a consequence of sea ice retreat, as there's a high correlation between the Barents Sea open water area and heat loss, R 0.86. That is an excellent correlation. Excellent correlation. That's an excellent positive correlation. Using a representative heat flux of the open water area of 100 watts per square meter, most of the increased cooling, about 30 terawatts between 1900 and 2000, can be explained by more extensive open water area, reducing from about 750 square kilometers to 450 square kilometers. So this further supports earlier findings, and it gives some citation, concluding that the overall heat transport is the main driver of sea ice and heat flux variability in the Barents Sea, with positive OHT anomalies preventing sea ice formation, letting the heat escape to the atmosphere. Let's look at Figure 10. Simulated observed Barents Sea temperature, sea ice variability since 1900. Observed is in orange, simulated is in black. And then B is the annual mean sea ice area. Okay, so let's take a look at this. So the upper panel shows the temperature anomalies observed in the models, and you can see the model closely follows the observed, but look. Let's see. Show you what the years are. Yeah, look at what's happening starting about 1960, 1970. Look at that. This is a major positive slope there. That is a major increase in the temperature. Major warming going on here. And overall, there's a warming. So you're going to have a positive slope, but you're going to really have a positive slope for the last 60 years or so. Right there. Now, that then corresponds, and this is average temperature of 4 degrees C. That's the average anomaly temperatures, meaning that it has warmed up on average 4 C. That is a significant warming. And then they look at the sea ice area in millions of square kilometers. And we can see, again, starting from 1960, it's just decreasing significantly. According to some of the models, it's been decreasing over time. If you look at some of these other studies being done, really just showing seasonal variability up until 1960. But then when we get from there, we see a clear decreasing trend. A clear decreasing trend. Very important graphic. This is an important graphic showing the direct relations between the warming waters melting the ice. And therefore, you get the heat fluxes as explained in the text. Polar sea heat loss also increases steadily over time, with the tripling from 7 terawatts in 1900 to around 21 terawatts in 2000. The annual mean heat flux remains below 3 watts per square meter, mostly explained by long-lasting sea ice cover and net sea ice growth. So again, this is for that 100-year period. Things have rapidly changed in the last 20 years. And then they proceed to talk about dense water formation. Basically, as the waters warm up, the dense water formation is decreasing. So as we mentioned earlier, we're not getting that mixing way down into the basins, but stopping at intermediate depths. So the dense water formation is reducing. So figure 11, impact of ocean changes on the northeast Greenland ice sheet. And figure A is figure A is the Norwegian Earth system model. And figure B is simulated advance or retreat. The determinist position in black is based on the parameterization described by Slater et al. In 2019. So what do we have going on here? So this is looking at the mean summer subglacial discharge in cubic meters per second. That's this orangey line here. And this is the Northeast Greenland shelf, 200 to 500 meter temperature. And really not much correlation until starting about 1980, 85 or so, where we see the discharge is starting to track closely with an increase in temperature. And then the Tidewater Glacier terminus position. And basically what we're seeing is a decrease in the positioning. In other words, the ice is being lost. This to me right here, that's the important, that's a very telling aspect right there. Now they start going to the last decades. So, where I was kind of criticizing them on was probably a little premature, because they're looking at the 1900s, they're looking at 100 years, and things have drastically changed in the last 20 years. There is low positive correlation with the local wind forcing, suggesting a contribution from simple Ekman transport dynamics toward the Norwegian coast. The baroclinic transport of the western branch is calculated based on equation 2 with the Coriolis parameter for 60 degrees north. Okay. Coriolis parameter is basically how much deflection, because the Coriolis effect is a deflection to the right in the northern hemisphere. Well, that's a function of latitude. And basically the Coriolis parameter takes into account as part of the parameter what the sign of the latitude is. The Coriolis effect right on the equator is 0, because the sine of 0 is 0. Whereas the sine of 90 degrees, or pi over 2 in radians, is 1. So the Coriolis effect is most pronounced at the North Pole, And since 60 degrees north is pretty damn close to the North Pole, we're going to see pronounced Coriolis effect, in other words, pronounced deflection to the right. So, the values are from sine 0 to sine of 90, which is from 0 to 1. They use a reference density of basically 1,027.5 kilograms per cubic meter. When we do TS curves, we drop this 1,000 stuff. We just look at the 20. We just look at this, these digits right here. So the Arctic heat loss in watts per square meter. Let's take a look at this figure 12. Inflow toward the Arctic Ocean is a function of heat loss. Okay, correlation. This is important. The correlation coefficient is 0.78. That shows a positive correlation. Notice they're given correlation coefficient. They're not given an R squared value. R squared is how well the data fits the curve. They're looking at a correlation. They're basically showing that, yeah, we have a correlation going on here. And what's that correlation? Total Arctic Ocean volume inflow in sphere drops. So as we increase this, and then the Arctic heat loss. And this various researches here, but we see a trend. We have the volume flow has increased, the water is getting warmer, and therefore that's leading to increased ice melting, which therefore leads to increased fluxes of heat to the atmosphere, leading to a warmer atmosphere. This is part of the Arctic amplification. So that's basically what this is telling us. And that's basically what they're trying to say that was happening in the last 20 years, is that the flow of water is increasing. The water is warmer. So therefore, we have an increased heat flow into the Arctic Ocean. That increased heat flow, depending on the mixing, how it mixes, how it cools down, does it cool down immediately or not? We now know that it's not cooling down immediately, so that the warmer water is reaching further into the Arctic Ocean. That is melting the ice, preventing the ice from forming in the first place. And if you have no ice, no cap, and with warmer temperatures, you're going to have an increased heat flux to the atmosphere. That's what's happening here. In the past, the water flow was less, the temperature was less, and then the ice didn't melt. So you had the ice cap preventing any heat flux into the atmosphere, keeping the atmosphere colder. That's all changing. That's what this is showing. And then figure 12 is continuing, and they look at coastal effects. And they use color codes to indicate what year that the data is coming from. As you can see, in 1900, it's all down here. When we get to 2000, we see what? We have an increase in the flow rate, how much, the sphere drops. Okay, this is the wind in meters per second. They're looking at wind forcing. That's what they're looking at here. And what we see is that there's a bit of a correlation here that's increased over time. Arctic sea ice loss, CO2 impact. Basically, if you lose the ice, it allows for increased CO2 uptake. That's the best way to sum up this paragraph. Okay, so now they get into the discussion aspect. Our review and analysis presented 5 main results over the last century, summarized with a simplified sketch in Figure 1. A majority of the Arctic Ocean heat loss occurs in the Nordic seas, where the Atlantic water is warmest, and the variability is directly driven by the atmosphere. Wind forcing. That's what this one is trying to indicate there, that figure. B, production of dense water flowing southward towards the North Atlantic across the GSR has remained fairly stable, but there is a small volume increase and recent warming. C, increased Arctic Ocean heat loss has increased the overall CO2 uptake. D, warming waters on Greenland's continental shelf affect melting of marine terminating glaciers in northeast Greenland. E, the Arctic Ocean sea ice cover is shrinking, and there is a related increase in overall heat transport and ocean heat loss in the Barents and polar seas. So now they go and look at some of these differences here. Generally, heat flux is larger in the east than in the west, caused by the larger temperature contrast between the warm Atlantic water inflow and the cold Arctic atmosphere. The heat loss values are largely consistent with earlier estimates stating that the Nordic seas dominate the heat loss. Temporal variability of heat loss. The overall Arctic heat loss increases over time. The heat loss trends over the last century are mostly found in the Barents and polar seas, reflecting the sea ice retreat and expansion of open waters there. That means, basically, what they're basically saying is all this heat loss, we're talking about heat loss from the oceans to the atmosphere, warming the atmosphere. That's what they're talking about. This is part of the reason why the polar region, the Arctic, has warmed 3 times faster than the rest of the planet. And now there's new papers saying, well, if we look at from the Arctic Circle to the North Pole instead of 60 degrees to the North Pole, it's 4 times higher the rate of heating. That's another discussion. There's also been sea ice loss in the Nordic seas. Only a small, not significant trend in heat loss. The major explanation for the different heat loss and sea ice relationship in Nordic seas is that sea ice loss occurred in regions cold surface water. Regardless of the small heat loss trends in the Nordic Sea, it is here where the bulk of the heat loss takes place. All part of the Atlantification of the Barents Sea, all part of the increasing Atlantification of the Arctic Ocean. Nordic seas dominate the year-to-year variability directly forced by the atmospheric circulation. Translation: Arctic Oscillation, Arctic Dipole, North Atlantic Oscillation. Sea ice loss is similar to observation-based Arctic sea ice reconstruction, and they cite Walsh et al. Well, this is John Walsh. John Walsh was the lead author on the paper that formally described for science the existence of the Arctic Dipole, of which I am proud to say that part of the research I was doing with sea ice helped lead to the discovery of the Arctic Dipole. So my little minor contribution to the science. So they discuss here temporal variability of Arctic sea ice cover and all the particulars and nuances of that. The Barents Sea ice decline between 1900 and 1950 is thus consistent with observed increasing temperatures, and we now know that that is increasing even more so in the last couple of decades. Overall Arctic heat loss variability contributes to variations in overall heat transport over time. Heat loss explains a large portion of variability since 1900. Okay. These heat flux values lead to a surprisingly good fit with the NESM values, with an increased Atlantic water inflow from 9.5 to 11 sphere drops. An increase in the Atlantic water overall heat transport has been found as a consequence of increased CO2 forcing using a coupled climate model. As discussed above, a majority of the overall heat transport increase over the last century explained by the increased Atlantic water volume inflow, as temperature changes were minor and the overall heat transport across the other Arctic straits remained stable. This is consistent with new short-term results from farther south in the subpolar North Atlantic, which also find the overall heat transport to be primarily dictated by Atlantic water inflow. Recent work confirms a high overall heat transport northward through the Nordic seas over the last decades, with an estimated Arctic Ocean heat loss of 282 terawatts. In other words, less ice, more heat to the atmosphere. And remember, these are totals based on integrating over the surface area. You get a good handle when you look at the watts per square meter per unit time. That gives you the flux. Okay? So this is overall, but still, that's a bit of heat. And they proceed to go through a whole bunch of, looking at other studies, what they found, all the nuances and so on. They bring in the AMO, Atlantic multidecadal variability, as driving some of the sea surface temperature variabilities in the Atlantic from the equator to about 60 degrees north latitude. And that's a perfectly legitimate thing to be mentioning. They say we may conclude, based on all this discussion, that the overall heat transport has increased over the last century and appears to have peaked temporarily. I'm going to contend that. I think we're seeing an increase, especially in the more recent years, of the flow rate as well as the heat being transported. Now, if they want to say that the flow rate has peaked and the sphere drops, okay, but the waters are warming, and it is bringing in warmer waters. Now, the other thing to remember, they're looking at a lot of the consideration is surface waters, and so if AMOC is slowing, which means the surface waters will be cooling, then okay, then that's a valid statement. But we know that the North Atlantic intermediate water, the source for it is the Mediterranean, and the Mediterranean is really warming up. So we're still bringing in that warmer water from the Mediterranean that ultimately finds its way going across the Fram Strait. So that's going to contribute to what we're seeing overall in the Arctic Ocean. Now, if they're talking strictly surface water, okay, then I'm not going to quibble much about that. But you need to include the North Atlantic intermediate water. And now that I'm thinking about it, I'm not really seeing in this review that factor being taken under consideration much. Wind forcing. Several studies show a strong link between the Atlantic water inflow and large-scale wind forcing in the region. And they go through, again, some more studies that they cite. And now we get into implications and warming and so on. So let's take a look at that. Implication of the Arctic heat loss, sea ice, and overall heat transport. The discussion above summarizes a combined consistent relationship between Arctic heat loss, overall heat transport, and sea ice cover. Over the last century, the heat loss and OHT increased while the sea ice cover decreased. The relationship was perhaps expected based on analytical model. Clearly, the inflowing Atlantic water overall heat transport anomalies are not fully escaping to the atmosphere through cooling in the Nordic Sea, but some surplus heat is left and continues onwards into the Barents and polar seas. Our main hypothesis listed in the introduction was that the inflowing OHT Atlantic water anomalies influence the ocean heat loss, deep and intermediate water properties. Oh, now we're finally getting, other than a passing thing about the mixing to depth and so on, now we get a little reference to intermediate waters. And then, the Arctic sea ice cover. We established that there is an analytical relationship between the Arctic sea ice cover, ocean heat loss, and overall heat transport. Less sea ice allows a larger heat loss, accommodates a stronger overall heat transport by the Atlantic water. Arctic sea ice loss is one of the well-established consequences of global warming, increased CO2 levels in the atmosphere. And the ocean heat loss and OSC therefore also change with global warming. How would this have played out without global warming? A natural climate variability strong in the Arctic Atlantic sector. We speculate wind forcing would then have dominated the variability. Atlantic water inflow is partly wind-driven, Arctic dipole, Arctic oscillation, North Atlantic oscillation. We found an increased wind-driven Atlantic water inflow. This increased OHC would then alone have contributed to ice loss, especially in the Barents Sea. And they look at what goes on with the Greenland glaciers. It's warming, it's melting. We know that. We know that if you don't have the ice cover, that therefore there's an increased atmospheric water interaction, allowing for increased CO2 uptake, which is then temperature driven. Warmer waters, less uptake. cooler waters, more uptake of CO2. And, so you can see a spatial, regime in that, with the increase being higher on the towards the Pacific side than on the Atlantic side, because the Pacific side has cooler waters. And talk about some of the differences in the values being uh, uptake, and how that translates into megatons of productivity per year, and undersaturated waters, oversaturated waters. As you keep warming up the waters, you could eventually cause an outgassing of CO2 back into the atmosphere. So, the conclusions. Global warming and Arctic sea ice loss have been ongoing, well documented for at least 30 years. The Arctic sea ice loss is consistent with a larger loss of heat from the ocean to the atmosphere, mostly in the Barents and Polar Sea, but we're now starting to see that in the Kara, Laptev, and East Siberian seas. This increased heat loss from the inflowing Atlantic water is in itself connected to a larger inflow of Atlantic water. However, there's additionally been an increased wind forcing. Well, if you have less ice there, then the wind is going to impact the waters more so. So when you have the wind forcing, you're pushing the water, you're going to increase the flow rate. That's basically it. And they're saying we have an increase about 1 sphere drop, 1.5 over the last century. This increased Atlantic water volume inflow is the main explanation for the increased heat transport to the Arctic Ocean from about 150 terawatts to 200 terawatts today. That's basically a 33% increase. The partitioning between overturning dense water and overflow water formation, horizontal boundary current, polar water formation, has remained roughly equal, but temperature variability plays a larger role in the overturning part. So there it is. It's right there. Increased flow rate, increased water temperature, increased sea ice loss, increased heat loss from the waters to the atmosphere. That's what they're talking about here, warming the Arctic. And don't forget, with the intermediate water, the role it plays. The gradual cooling of Atlantic water as it circulates the Arctic Ocean from its entry across the GSR mostly occurs in the Nordic seas. The year-to-year variability of this winter cooling is dictated by the atmospheric forcing manifested in the variability of currents of low-pressure systems over Scandinavia, which drive cold air outbreaks, CAOs. Low-pressure system. That's a reference to the NAO, North Atlantic Oscillation. Sea ice cover of the Arctic is set to further decrease in the future. This will contribute to more open water and a larger ocean heat loss. Important statement. Sea ice cover of the Arctic is set to further decrease in the future. This will contribute to more open water, larger ocean heat loss, in other words, further warming the atmosphere, leading to the Arctic warming 3-4 times faster than the rest of the planet. Future production of dense water is more uncertain, as wedged between the increased heat transport in and the larger heat loss at the surface. There's an addition to natural climate variability exemplified by the wind forcing of the Atlantic water and the CAOs, right? The cold air outbreaks. These fluctuations are difficult to tease out. So, what are they basically saying overall? Wind stresses helps increase flow of Atlantic water into the Arctic Ocean. The Arctic Ocean, the Atlantic water is warmer. Increased flow, along with increased warmth, increases the heat content coming in to the Arctic Ocean. A lot of heat loss takes place in the Nordic seas, but more and more of it is remaining intact to flow further into the Arctic Ocean. This heat is basically helping reduce the sea ice cover. We now know that it's preventing ice from forming. It's melting ice earlier. When we have more open water, you have more heat loss from the ocean to the atmosphere. That's what they're talking about when they talk about heat loss. That's the flux of the heat contained in the ocean, in the water, moving into the atmosphere. That allows for CO2 uptake. So this is kind of interesting because, as I mentioned earlier, if you lose the sea ice, you're losing two major areas of productivity: ice algae and ice edge productivity. But now they're saying there's a possibility that allows for increased uptake of CO2, which phytoplankton need to do photosynthesis and increase the biomass. So perhaps that is a compensatory aspect there. To me, the factor then is, what is the elevation of the sun in the atmosphere? Is it sufficient to activate the photosynthetic process? That remains to be seen. So we're seeing increased heat. The heat melts the ice, prevents the ice. It's now making its way further inward, affecting the rest of the polar. This is basically what I've discussed with you guys in numerous videos before. So think of this as kind of a synthesis, trying to pull it together. Now, their analyses were looking at surface water. I basically give the reminder to remember the intermediate water inflow into the Arctic Ocean as well. Because, yes, the surface of the North Atlantic does appear to be cooling because of the slowdown in AMOC. So, yes, we might start to expect to see a slight decrease in heat content of surface water, but you still got that intermediate water whose source water is the Mediterranean, and that is still flowing in. So that more than compensates for any cooling of surface heat content. The Mediterranean is really warming up. So increased flow, increased heat content, keeps the seas open. Heat diffuses to the atmosphere because the water is warmer, and due to the flow regime, the heat doesn't all get lost in the immediate Nordic Sea, but continues further into the Arctic Ocean, which will then affect the ice further along in the Arctic Ocean. Eventually, that heat will then also make it to the atmosphere. That's basically the take-home message from all of this. They looked at it from 1900 to 2000, and then the last 20 years, and we see this uptick in activity in the last 20 years, really starting to increase what we're seeing, what is happening. So, as I said, I will leave the URL for those who. This is a deep read, and I could not really take all the time to go into this. Otherwise, it would be a 4-hour video, and you guys would get sick of my voice after a while. But there's a lot of information in here, and I tried to outline I tried to summarize in general terms here what is happening, what has happened, and the current trends and where it's headed. But as I said, the take-home message is that the flow rate is increasing. That's wind-induced. The water is also warmer, at least until perhaps the last couple of years for surface water. But the warmer heat, increased flow is keeping the Barents open, is melting the sea ice sooner, is preventing the sea ice from forming. That allows the heat to diffuse to the atmosphere, warming the atmosphere even more so, warming the Arctic more so, leading to Arctic amplification. So this is basically in agreement with all the other videos I've shared with you and discussed with you of what's taking place in the Arctic. And remember, what happens in the Arctic does not stay in the Arctic. It will be felt globally. Thank you for your time. Thank you for your patience as we did this deep dive into this topic. But this is a very important paper. We'll talk soon. Hello folks, this is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.